I'm gonna record to the cloud. Hopefully it doesn't run out of space. Okay, awesome. So first section that you guys have for chapter 11. Wow, that's like super small. So we have chapter 11, which is alkynes. Just going over what an alkyne is, it's pretty much the triple bond. This is made up of, this is made up of 2 pi bonds, which are made from overlapping p orbitals, and then 1 sigma bond. The way that you draw a triple bond is like this, and that's because the geometry of this is 180 degrees. And these are sp hybridized, which you guys went over in like chapter 1. Remember, you guys talked about it in chapter 1 material. So that's pretty much just what an alkyne is. There's like terminal alkynes and there's internal. So the one I drew over here is internal. If it were at the end, something like this would be a terminal alkyne. And then there would be like 1 hydrogen on it, and we'll see how what the pK is for that in a little bit. So the nomenclature for this, you kind of just change the ane ending to so let's say that we have like this 2, 3, 4, 5. So this would be like pentane. Say that you moved it to this. So you have 3 carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This would be pent 1 ine. So you can kind of just see how I have the triple bond is at the 1. Numbering is kind of the same. The triple bond does have priority over a lot of different things. So that you have like 2 methyls or something on the like this, and obviously triple bond would have priority, so you would have like 1, 2, 3, 4, 5, and then it would become 4 dimethyl pent 1 ine, like that. Cool. Any questions about nomenclature? You kind of just get that kind of stuff with practice. 11.3 has like stuff about physical properties. He doesn't really test on stuff like that. Interesting, alkynes never really asks about stuff like that. And then we have preparation of alkynes. So this is kind of like how we make them. So linear preparation of alkyne. An example would be something like this. So let's say that we have this compound, and then you have 2 chlorines or halogens. So this could be like bromine, iodine, pretty much anything like that. And then you would do something like 2 Na plus NH2 with 2 HCl, and this is just our strong acid catalyst, and you would get something like this. And make our beautiful alkyne, just like that. And then another example is when you just have 2 halogens across from each other on like adjacent carbons. You can use something like K plus O, C, CH3. Do you guys remember what this is?
Terpetoxide.
Base.
Bulky base, terpetoxide. and then 2 HBr as the catalyst. And from this, you're making your beautiful alkyne. So something that you can ask as like an exam question is, what reagents would you need to convert this? This is supposed to be cyclohexane. Okay. To convert this into over here, you're adding on a little pi bond. And so in order to do this, first step should be, wow, I really should have been doing these on Notability the entire time. It's much easier. You can add Br2, and that's going to add them across the double bond like this. It's actually going to get rid of the double bond. So it's going to use those electrons to add them on there, and then you can use Na plus NH2. So that would make the Na kind of like have a minus charge on there. Use 2 equivalents of this. Definitely pay attention to how many equivalents you're using of these molecules, because that will probably show up on the exam. And then that is what the answer would be. So the answers would be 1 Br2, 2 NaNH2, 2 equivalents. So is everybody good with that?
Are the NH2 like 2 equivalent and like NaH like interchangeable or no?
What is
Like
the question? Sorry.
Like NaH and NH2, are they interchangeable? Because aren't they like kind of doing the same thing?
Yeah, so I'll go over that in a second, what the strong bases are and what like isn't super strong. But yeah, we have, I'll do that like right after we talk about the addition reactions. So that was preparing them, and now this is one of the types of reactions that they go through. So they have addition reactions. We have addition reactions. So this is when you're getting rid of the triple bond, which makes sense because when we were doing addition reactions before, they were getting rid of the double bond. So now we're getting rid of the triple bond. So over here, we actually make a alkene intermediate where this adds it like this. Okay, there you go. So we have X and Y. And so this can be something like HCl, just as an example. And then you're adding another X to Y. And then you're adding this as your final product. So you have X and Y and Y. And you're adding 4 sigma bonds. So just as the 4 addition reactions, so that's like kind of like the basis of all of them. But the book has this like super awesome chart that looks like this, where we have a terminal alkyne, just like that. If you have 2HX, and then the X can be Cl, bromine, iodine, then you have a compound that looks like this. You're adding all your hydrogens on there. Then you have your halogen, and this is called hydrohalogenation. I'm not 100% sure if he would like need you to know the name for it, but I would just in case. I feel like knowing the names helps me at least. And then over here, we're adding just like a ton of our halogens. So this is called halogenation, fitting. Then we have over here H2O, H2SO4, HgSO4. This is an interesting one because you end up adding double bond O on there. The rest of them are just H's. This is called hydration. Also fitting, because look at that, you're adding a water molecule onto there. And then over here, this is a two-step reaction. You're adding R2BH, 2 is H2O2, and then OH. And then from this, you have oxygen, hydrogen. These are really helpful to make like cheat sheets. I feel like when I was studying, I would always make sheets like this so that while I was actually doing, oxidation, while I was actually doing practice problems and stuff like that, I feel like it's helpful to have something to reference. So I would always reference these sheets that I made for myself. So yeah, obviously the book has like a much better organized picture, but for the sake of time, this is what my beautiful drawing looks like. This is the next thing that we're going to talk about, which is terminal alkynes reactions as an acid. So this is kind of taking like a lot of the things that you know and that you've learned from since like the beginning of the semester and putting them into one question. So you guys learned at the beginning of the semester that this hydrogen over here is, I'm actually going to put it in a different color so you guys can really see it. This hydrogen is pretty acidic. The pKa of a terminal alkyne is 25. And so something that you might want to do in a reaction to kind of like add on to this is make this look like this. So you're going to deprotonate it, and that puts on a negative charge, but only specific bases are strong enough to do this, and those two bases are NH2 and H minus. So you might also see these as like Na, NH2, which we just saw earlier, or NaH. And so the pKa values of these are 38 and 35. So they're stronger bases. So they're able to deprotonate it. Some things that are not strong enough, I don't want to confuse you guys, but let me just tell you guys the pKa values are things like OH or OR. So it's like oxygen, like a carbon chain on it. So this has a pKa of 15.7, and this has a pKa of 15.5 to 18. So obviously, those are not strong enough bases to deprotonate the hydrogen. So is everybody good with that?
Yes.
So this is a way to make a nucleophile. So this becomes a nucleophile. So obviously, it's ready to donate some electrons. So then addition of hydrogen halides. There are a couple ways to do that. And there's also mechanisms. I feel like we can go without the mechanisms. Let's do addition of. You can have a terminal one, or you can have one that's like actually not terminal. What is it? Internal? Yeah, that's it. Okay. So then, let's say that we have HCl that's going to, like we saw earlier, in that addition, we would add it across, and then if we were to do 2 equivalents of this, then that would completely get rid of it. So then we have H and H, Cl and Cl. So then the final product, without actually drawing it with those hydrogens, and I'm not making it straight anymore because you don't have to. That's what it looks like, but let's say that we have a terminal alkyne. So we have like that hydrogen over there. Let's say that we're doing it with bromine this time. Then we have, so we have our hydrogen from last time, and then our new hydrogen, PR. If you do another equivalent to completely get rid of any sort of pi bonds, then you might get something that looks like this. And then you have all these new hydrogens. And then this is actually what it would look like. So pretty cool. If you were only to add one equivalent, then this would be your product over there. So kind of just pay attention to that. Book has the mechanisms, so those might be helpful. And then we have additions of halogens, and that's when you kind of form that bridged polonium ion. It kind of looks like an epoxide, and you kind of have to open it like an epoxide. I'll let you guys look at the book for that mechanism, but just as the basic mechanism. You might have something like this. So let's say that we're adding something like Cl2. Then you have this, and it's adding across the bonds. And then let's say that you have another equivalent of Cl2, and that also adds across the bond. And you have like so many Cls, and this is actually what it looks like. And Cl. Any questions about that? Do you guys want me to do the mechanism?
No, it's okay.
So then we have addition of water, and this is where learning all of the Markov and anti-Markov comes in handy. And I know it might look like a lot of mechanisms to know, but you guys only have to really keep this information in for so much time. What is it, like 2 more weeks, and then you guys can dump it. Which I'm not like telling you guys to do that. I'm just saying that it is an option. So this is another one of those reactions. And this is in the enol form, but we know that which one is more stable, the keto form or the enol form?
The keto form.
Yeah, awesome. So if we were to draw the arrows, it would look like this. I also think that he would ask a question like this on the exam. So over here, let's say that we're adding it onto a terminal alkene. We have HDSO4. And again, adding it onto enol form. But keto form is more stable. And this is the Markovnikov addition of water.
So you
Oh,
only,
just, sorry, what's the question?
so when you're adding water, you only need the HgSO4 when it's terminal.
That is what I'm understanding from the book, yes.
Okay, thank you.
So I think it's just there as like an extra catalyst, but technically the only thing that you're really using is water when you're doing these types of reactions, to be honest. Like if you look at the mechanism of tautomerization in acid, I guess you do need it. Okay, wait. Yep, the only thing that you're actually using is the water, but it seems like you do need to have the HgSO4 there as like a catalyst. So yes, just as a little recap, this one is the enol form, and this will come back to haunt you even in Orgo 2. Maybe don't forget the keto and enol stuff just yet. Just know that keto form is more stable. And remember what it looks like, and you can kind of tell because look, there's like a ketone right there. This one doesn't have a ketone. That's just nothing. As an alcohol. So you have a hole.
Whenever we see an enol, do we know like we have to make it into a keto or into keto form? Or are there like cases
I feel like
as an enol?
he might have a question that's like straight up like, what is the keto form of this enol structure?
Okay.
Because like that's how I guess like important it is. Just know that there are like more keto forms in nature kind of thing.
But like in terms of synthesis, if we have an enol, should we make it into a ketone form?
The answer will be there.
Okay.
But if the keto form answer is there, which I don't think he would do that, like give you both the keto form and the enol form. But if he did, I would probably pick the keto form.
Okay.
Unless it specifically says in the instructions something about like pick the enol form. Cool. So next we have hydrobor, again, fluoration, oxidation. Have fun. And I would say that he's going to have most questions from chapter 11. If I'm being completely honest, like if I were to pick a chapter to like really focus on, it would be this chapter. So yes, hydroboration is using BH3. Oh my gosh, I remember this being so much fun. Okay, so you have I'm trying to figure out what the best way to explain this is. Okay, so basically you have an internal alkyne, and you can add some BH3 on there, and this is a two-step, so you do have to pay attention to the numbers here. And OH minus, then that turns it into OH and H. And I know it looks weird if you do like BH3. Oh my gosh, I'm gonna get to add bromine or something like that. Nope, you don't. But again, over here we're seeing that ketone and keto and enol forms. And let's say that we have a terminal alkyne like that. For this, you would add R2CH. And again, this is a two-step thing. H2O2 OH. Then you get to add your enol like this. And then you actually don't get a ketone from this, you get an aldehyde.
What do the long arrows and short arrows mean? Does that just mean like the long arrow favors the keto form or the aldehyde part?
Exactly. So an equilibrium arrow looks like this, but over here we're doing a long arrow and then a short arrow to show that there's more going towards this side. Yeah, so that's pretty much what that means. So over here in the book, it's saying addition of water using H2O, H2SO4, and HGSO4 forms methyl ketones from terminal alkynes. Addition of H2O using an organoborane, then H2O to OH forms aldehydes from terminal alkynes. So you can form a ketone, but you have to do it with this. So let's say that we have this terminal alkyne, but instead we use H2O to, H2O, H2SO4, HGSO4. And then from that, you get this. And then you would get your ketone. So you just have to really pay attention to what type of agents you're using. Cool. Everybody good with that?
Yeah, thank you.
Awesome. So let's see what is important from here. Oh, actually, a lot of stuff is important here. You definitely ask a question on really anything here. So let's just do an example for reaction of acetylide anions. So we have reaction. And obviously you wouldn't just like make an acetylide anion just to like make one. So usually they're going to partake in reactions. An example of them partaking in a reaction. So let's say that we have our nice little, okay, let's do it just like this. So it's just our nice double bond, and let's say that we want to react it with NaNH2, and then CR like this. So let's go ahead and number them. And then let's say that we're making a question mark, and let's say that we want to react it again with NaNH2, and then second with this Cl that looks like that. Let's see what the question mark looks like. So first thing that we're going to do is, okay, well, actually, let me do the mechanism for you guys. So we have NaNH2, which pretty much just does this. That's going to take that, move those hydrogens over there. And then we have this. Then we have this thing that looks like this. It's loving my descriptions. This thing that looks like that, and that thing that looks like this. So pretty much make sure we count our carbons. So we have 1, 2, 3 carbons that we need to add on. So we have 1, 2, and 3 carbons that we have to add on like that. And then next we have this structure. And then let's start on part 2 of this reaction. So again, we're going to go ahead and pull off that hydrogen. And we do this. Then we have our Cl that looks like that. and we attack the carbon that it's on. And that chlorine goes away. And then we have 1, 2. Now we have to add on. I actually feel like this was a question on my exam when I took it, too. And that is what the final product is. So that's kind of just an example of the mechanism. I also recommend going over the stuff with epoxides. She doesn't really like epoxides. So I'll let you guys do that. Definitely go over that stuff. And then synthesis. Let me think what he would ask about that.
Do you mean like with MCPBA or?
What do you mean about MCPBA?
Like for adding epoxides? Is that what you mean? Like,
Pretty much just like anything related to epoxides. He really, but I'm talking about the epoxides relating to the acetylide anions and how they open up the epoxide rings, and pay attention to stereochemistry when you do those types of questions. Cool?
cool.
Okay, synthesis. In lecture, when you guys do worksheets, or when you guys did worksheets, he might have stressed talking about, what is it called? The reverse synthesis, like the heterosynthesis reactions. He wouldn't really test on that on the exam, but I do feel like if you have time, it kind of helps to figure out the heterosynthesis and then put in reagents. That's like if you feel comfortable enough doing it. I don't recommend doing anything that you're not comfortable doing on the exam. Okay, so now chapter 12, we have oxidation and reduction. So we have oxidation, just like our basic oil rig. Oxidation is loss of hydrogens and then gain of like oxygens, obviously, because you have like oxidation. And then you have reduction is gain of hydrogens and also loss of oxygens, and this is kind of just like C to Z bonds in general. And this is like carbon to H bonds, not just like hydrogen. So comparing like alkanes to alkynes. Alkanes are the most reduced, and then alkynes are the least reduced. You wouldn't really ask questions like that. Actually, let me see what kind of questions he asked. He doesn't really ask much about oxidation. I'll ask about, polymers. He asked a lot of chapter 11 questions. Yeah, pretty much for this entire chapter, the biggest thing that he asks is, this is the before compound, this is the after compound. Which one is reduced? Which one was oxidized? That's the extent of the questions he's asked in the past. And so I'll do those questions.
You mean like the
How
ones
about-
that show that before and after, and then ask if it's reduction, oxidation, or neither?
Yes, pretty much. But he'll ask them in like kind of annoying ways where like for A, B, C, and D, they're all different compounds. So it's like you have to like go into every single one and count the hydrogens and count the oxygen kind of like CZ number. How about I skip over chapter 12, go to chapter 13, and then I'll show you guys the type of questions he asks for chapter 12. I think he asked maybe like maximum 4 or 5 questions for chapter 12 when I took the exam. They really like were not hard at all.
And does he like touch base on 13, or is it mostly chapter 11?
Yeah, he does talk about chapter 13. He'll do like descriptions and then talk about which of the following structures is consistent with a compound that displays these peaks. A prominent M18 peak in a mass spec suggests the compound might be a blank. So he might have an actual IR spectrum on there and ask you guys what the compound is. The question that I had on my exam was taken directly from the worksheet that you guys have, which I'll throw up the worksheets in a sec. Yeah, this is another reduction question. This is another reduction question. How about after I just give you guys the important peaks that I think you guys should know while going into the exam, and then we start doing practice questions now, so we have enough time to cover all of them.
Okay. Yeah, that sounds good.
I'm also gonna move after I write these up. So the important ones that I think you guys should know are, I'm gonna put lines really quick. So that it actually looks nice for you guys. We have bond type, approximate, wow, that is a B. Approximate, what is that, wavelength absorption? I don't even know. It's in centimeters, -1. And then we have intensity. I remember the first thing I did when I took this exam was I kind of like brain dumped all of the numbers. So like the first thing that I did was I like memorized this chart and I wrote it down word for word so that when I was actually taking the exam, I wasn't having to like recall it and like second guess myself. Just very strong, broad. We have NH. This is going to be another 3,500 to 3,200. Going to be medium. Let's say that we have C to H. So we might have CSP3H. And Dr. Dowdy even mentioned today in class that this is kind of like a little bit harder to see, just because you'll have like the peak like this and then it's like super tiny like that. But anyways, let's just write it for the sake of writing it. So these are going to be at about 3,000. This one specifically is like 3,000 to 850, 3150 to 3,000. I have this one at 3,300. So this is they're all gonna be, they're all medium. In my notes, I have that the C to H is strong. So the way that it's like the peak is, it's like thin kind of. So you might have C triple bond C, and this is going to be at 3,300. This is going to be the first one is strong from my understanding. I can't even read my own handwriting. And this one is medium. That's what I'm going to say. It's what I'm getting from my notes. Okay, so then we have C triple bond N. This one is at 2250. I'm gonna throw myself off the cliff. This one is also 2250. I apologize if anybody's writing in pen. My bad, for real. So then we might have, this is Dr. Dowdy's favorite peak. So we have 1800 to 1650, but you're really just going to see it at about 1700, and this is a strong and sharp peak. C double bond C, you might see at 1650, and that's medium. And then if you see a benzene, then that can be at 1600 or 1500, and then that is medium peak. So those are like main ones that I would know going into the exam. So I am going to rush the restroom really quick, and then I will come back and we will finish. You guys good with that? Let's take a 5-minute break.
Yeah.
Okay, so somebody said, is it SP alkyne has the highest wave number because it is least reduced? Is it SP alkyne? You know, I'm not really 100% sure. And Dr. Dowdy tells you guys, like, don't memorize these numbers because he wants you to understand them. But they're just numbers. Like, there's nothing really to understand about them. If that's the conclusion that you got from it, I personally, my brain is not working enough right now to make that full connection. But maybe I can get back to you about that. Okay, so you guys, let me send in the worksheets really quick. Do you guys want all of the worksheets from this? Like 11, 12, and 13 worksheets?
Yes, please.
Okay. That is just the chapter 10 worksheet. They're not completed. I do not have the completed worksheets, unfortunately. But if you guys want, you can send me your worksheets and I can confirm or unconfirm, whatever is the word for that, unconfirm. Oh, that's a word. But let me send in the last worksheet right here. Okay, great. Those are all the worksheets. I hope you guys enjoy them. Are you guys ready to get into some practice questions?
Yes.
I'm gonna stop sharing that and I'm going to share a whiteboard. Just because I do feel like the whiteboard allows me to type up questions. And I'm gonna move so that I can charge my iPad. It's the whole room for you guys. Okay. So are you guys ready to rumble? Maybe I can put you guys on a table. Then I'm actually able to write. Okay, so question number 1. We have in green, such an ugly color. Okay, which of the following structures is consistent with a compound that displays a molecular ion peak at 103 and medium infrared signals?
There's nothing showing up on the screen.
It has to, I have to click enter.
Oh, okay, my bad.
It's okay, don't worry. But trust me, it's gonna look so much nicer than my janky handwriting. Okay, did nothing show up still? Oh wait, I didn't click enter. Oh wait, I did click enter. There you go. So much prettier than my usual handwriting, isn't it? Okay, so let's say that we have the first structure looks like this. We have C triple bond and B looks like this. It's an actual benzene with a C triple bond, and C looks like this. It's a benzene with a C triple bond C, and D looks like this. Cyclohexane with a C triple bond C. So breaking down our peaks, we have a C triple bond N peak at 2250. Okay, so we have 2250. That means that it's going to be C double bond N for sure. So it's not C and it's not D. And then our next peak is a 1500 centimeter, -1, and that's going to be a benzene ring, like we saw previously. So that means that our answer here is going to be B.
What about the 1599? Is that part of the 1500 like estimate?
That's kind of just like to throw you off, I'm pretty sure. But yeah, I think that benzene does have 1500 and 1600. So that's gonna, yeah, I guess.
Yeah, it's on the chart that you wrote.
Okay, yeah. So you have both peaks, 1500 and 1600. Everybody good with that?
How did you know that the 2250 was for the C double bond N and not C double or triple bond C because they're the same number.
True. I guess you have to like do the full ion breakdown and figure out that it's going to be nitrogen instead of carbon, which is literally a difference of, what is it, one number. That is kind of annoying.
Isn't it because of the odd molecular ion peak? Because it's 103. Doesn't that mean that
That is
there's
true.
nitrogen?
That is true, because it's odd. Yeah, because carbon is 12. So that means that every single time you're doing, you're adding 12. With nitrogen, is it 13? 14? 13? I want to say that it's 13. It's 14?
Yeah, nitrogen's 14.
Interesting. I feel like I have heard something about it being odd, which means that it's going to be nitrogen. And it was even in the worksheet today where you guys had 73, and that one was nitrogen as well, wasn't it?
Yeah.
Mhm.
So if
Yeah,
an
it's a
even number
rule.
of nitrogens, it'll be even.
Yeah. Yeah, so there's a rule. There you go.
I thought
Odd.
that oh sorry.
It's okay. What's up?
I thought that like the C triple bond and the C N triple bond, I thought they had like the same like I thought they were both like 2250.
Yeah, so they do have the same number, but over here they gave us the molecular ion peak, and it's 103, and because it's odd, that means that it's going to end up being nitrogen.
Oh, okay.
But
Yeah.
if it were like 104, I guess, or 102, then that would be carbon.
Oh, okay. Thank you.
Everybody good with that?
Yeah, thank
Okay.
you.
We don't pay
So
attention
next,
to the 1599, right?
well, the 1599 was the 1600 that we also see, because when we do benzene, there are two peaks for benzene. There's a 1600 one and a 1500 one.
Oh, okay.
Okay, so I'm gonna go ahead and type this question up. So just give me a second. I feel like it just like looks a lot better when I type it up, right? Would be strong enough to depro to make a terminal alkyne. So these are our options. We have A, tert butoxide. What do you guys think so far about tert butoxide? Yes, no?
Is it no?
Yeah, so for tert butoxide, that's not going to be our answer.
Is it because of the
And-
polar thing that you said? Like the ones that aren't strong enough?
Yeah, so this is when we were talking about how a terminal alkyne, does anybody remember what the pKa is?
25.
25.
Yeah, awesome. pKa is 25, so we're gonna need something that is a strong base, so the pKa has to be a little bit higher. So we discovered, like, we didn't discover anything. The book said that the two things that are able to deprotonate a terminal alkyne are NaNH2 and NaH. And that's because their pKa's are like in the 30s. So just going over the mechanism for this really quick. We have NH2, and that like kind of dissociates from the Na, which becomes like positive, and then takes the hydrogen, moves it like that, and then we have this. Wow, I can't. How do you? Okay, there you go. Perfect.
Are these
Everybody
like,
good with that?
are these like your old test questions?
I am not going. These are just some practice questions. How about that?
Okay.
Yeah.
Practice questions. Okay, are you guys ready for the next one?
Yeah, you know how Mr. Dowdy says practice, practice, practice.
These are just some practice questions. So the answer here is B. Everybody good with that?
Yeah.
Okay, next. So I'm going to type this question as well. So bear with me. for a moment. We have which of the following represents a keto enol tautomeric pair. So over here we have option number 1. And B. And this is what I was talking about, like how he would ask one of those tautomer questions. And does anybody know how many hydrogens keto and enol forms differ by?
Is it 1? I thought they didn't differ.
How do they differ? By 1 hydrogen and something else.
Isn't it a CH bond? A new CH bond?
So they differ in terms of 1 double bond and 1 hydrogen bond. Or sorry, 1 hydrogen. And then they are constitutional isomers, not resonance structures.
So what do we see?
So you already have the answer for me? What do you guys think that the answer is? Do you guys want to count the hydrogens? So over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 hydrogens. Over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Does this one have 10 as well? We have to count that one. So that one also has 10. Over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's not B and it's not A. Let's do D. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, let's do this one. So this one has 10. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do they not differ in the terms of a hydrogen? Did I make up that rule?
Yeah, I thought the double bond O and the H just switch spots when going from enol to a keto.
Yeah, it's definitely C. I guess the hydrogen rule is just I don't know where I got that from.
I know in the book, in the solutions manual, it's section 11.11 for anyone who wants to look at it after. I noticed that the keto enol, usually the double bond is on either sides of the OH. So that kind of helps me visualize what the keto would look like in the end.
That's kind of just like what it looks like, if that helps anybody. I realize what the keto and enol form interchangeably look like, and you can literally see it in C. This is one of those that you just look at it, I guess. Ignore my whole hydrogen rule. I thought I was a chemist.
What I went based off of was like the double bond has to be close enough to like move. I guess it doesn't really move, but
yeah, like when I was looking at it in the book, I was like, oh, it couldn't be D because that like double bond was too far away. I'm not sure if that's like a real reason for it though.
That does seem like it seems like a legitimate reason to me. Yeah.
I guess maybe it's also like resonance shift.
They're not resonance structures. They are constitutional isomers, which means that it's not a movement of electrons, it's a movement of like actual elements. I'm typing up the entire next question because it's a typing question. So ketone, ND, alcohol. Okay, so who wants to answer this question for us and give us a reason as to why the answer is the answer?
Is it an alcohol? Is it D? It's like
Why?
18 was like for H2O.
Yep, so over here, the answer is going to be alcohol. Because water, which is mass 18, is a waste product in the reaction with alcohol. So obviously water is H2O, we have 16, and those are like 2 times 1, and that means 18. So in reaction with alcohols, water is a waste product. Is everybody good with that?
I'm sorry, can you explain
Yep.
that again? It's just alcohol because it's 18.
Yeah, so water mass weight is 18, is a waste product in the reaction with alcohols.
If it was like other number, like 16, it would have been like other thing, right?
Alcohol is the only one that I'm aware of that has this like 18 rule.
Oh, okay.
Cool. Everybody ready for the next question?
Yeah.
Okay, this one is a fun one. So, did you guys go over Lindler's catalyst?
Yeah.
Yes.
Yeah.
What chapter did you guys go over it in?
12.
12.
It is. Okay, so you guys definitely have to know those. There's like H2 and then Lindler's catalyst, and then there's also another one that's like super
PDC.
important. Mm-hmm.
And
Yeah,
H3, yeah.
Yeah, it was H2 with PDC is really strong, so it can go from like an alkyne to an alkane. But H2 Lindler catalyst and NH3 are not as strong, so they can only interact with an alkyne to make an alkene. And like the Lindler catalyst makes it cis. And one of the TAs said to like remember like Lin is sin, so it makes cis. And then the other one, the NH3, is trans because it's just the other one.
We can do the reaction mechanism, but you guys really don't know the reaction mechanism, if I'm not mistaken. It's kind of just like you know what the reagent is. Is that correct?
I think so.
Okay, so these are your options. This is 1. This is 2. This is 3. And this is 4. So you guys can go ahead and work it out while I also will be working it out. So this is our nice terminal alkyne. We have NH2 minus sign. Go ahead and take that. And then we're left with this. And then we have this one. You're going to go ahead and attack this carbon. I like to always count my carbons. So we have 1, 2, 3, and 4. That way I'm able to kind of match it up. So we have 1, 2, 3, 3, and 4. And on 3, we had a methyl. And then next step, we had H2 and Lindler's catalyst. And then that gives us answer 3. So our final answer is Is everybody good with that? And that is attacking this side of the reaction. So technically, if you were to do it the way that I have been drawing it, it would look like this. But if you just flip it around, that's how you have your answer. Is everybody good with that? It kind of just pretty much what Lindler's catalyst does is that it takes off one of the pi bonds and makes it cis. You had a question? Sorry, I cut you off.
Oh no, it's okay. I'm just like still processing the question. I'm trying to like make sure I understand it. You said, so we would be looking for the answer that has a cis product, right?
Yeah.
Okay.
So why wouldn't it be 2?
Because that'd be trans product.
Why wouldn't it be 4?
Not enough carbons.
Why wouldn't it be 1?
Because that would be, that's an alkane, not an alkene.
Are you ready for the next question?
Yeah.
Oh, these are always super fun questions. So this is determine which compound will react with sodium in liquid ammonia to form trans 3-hexene. And then we have a hexene B is 3. Sorry, you guys. It just, I wonder if in the recording they'll be able to see me actually write it, since I think it records my actual. Yeah, I can go back to the previous question in a second. 3-hexene and E trans 2. Let me see if I can space them. Oh no, you can't see E. It's okay, I'll draw it for you guys. But somebody said, yeah. Let me know when you're done.
Thank you.
So, the product that we are looking for is trans 3-hexene. So hexene means that we're going to have 3, 4, 5, 6, and then we have on 3 a double bond. 1, 2, 3. 3, we have a double bond like that. Liquid ammonia, so that means that we are reacting it with NaNH3. I guess it's like technically NaNH3 like that. And then let's go ahead and figure out what it looks like. So first we have cis 2-hexene. Hate drawing cis products. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Technically, it just needs to be cis up to there. Over here we have 3 cis, so it looks like this. Really ugly. This one looks like this. This one looks like this. And this one looks like this. So what do you guys think that the answer is?
Is it D?
Does everybody agree with Nicole that the answer is D?
Yeah.
Okay, great, because the answer is D. And so pretty much what happens is that we go from looking like this, that's like another way that you could draw it, to looking like that. Pretty much, that's just what the answer is. Is everybody good with that? I'm going to take a picture of this, and then I'm going to show you guys. But I'm pretty sure that this is just from your okay. Is it upside down? I hate that story. Let me lock the screen. Oh, that's not going to do anything. If I lock the screen, maybe I should unlock the screen and flip it around. Another thing that I can do is I can take it to Notability. I can insert the picture. And I'm pretty sure I can rotate it. Can I not rotate it? I can. Look. Quick thinking. So now we're looking at question number 7. It says choose the compound that matches the following IR spectrum. And over here we have an alcohol. We have a carbonyl. So that is the only one with an alcohol and a carbonyl. So that is what the answer is. Is everybody good with that?
Do you think he would be like mean about it and put like multiple answers with like a carboxylic acid group?
No, he wouldn't, because then you wouldn't be able to figure out what the answer is.
Oh, okay, good.
Okay, is everybody good with that? When you guys get into NMR spectrum, he can do something like that, but he would have to give you the IR and the NMR. So he might do something like that on the final. So just be prepared. Okay. So
Can I ask you a quick question from the last one? Sorry. Yeah. Why couldn't it be B? It's like the same thing, but it's in like an assist type of way. Isn't it the same thing as the D?
It is the same thing. Nope. B was hexene. D was hexine.
Oh, God, sorry.
Yeah, no problem. Okay, so are you guys ready for another question? Okay, so we have just classify the following reaction. I'm not sure when your exam is. I believe it's Thursday, though, maybe?
Thursday.
Yeah, it's Thursday.
So this one is classify the reactions. We have this first one, and this is just like as oxidation or reduction or neither. You guys can answer that. What do you guys think that first one is?
Would that be neither?
So we have a vote for neither. What do you guys think? So the way I like to answer these is I do like to write out the formula. So counting that, we have C6H10, and then over here we have, counting our hydrogens, C6, oops. We have C6H11Cl. So we're increasing the C, what was it, CY or CX groups that we're not supposed to have, but then we also have, so like if you write a little analysis, we have one more CH and also one more CX. So this means that this is neither. Awesome, you guys. And then if we were to do this one and count our hydrogens like that, then we would have C5H8O, and then counting this one, we have C5H8O2. So if we have one more oxygen, then what does that mean that this one is?
Oxidation.
Awesome. This is the oxidation. Any questions about this?
Wait, why is the first one neither? Because it has not one more hydrogen, or?
Yeah, so because you have both of them, it's going to make it neither. So the one more CH means that it's going to be a reduction, but the one more CX means that it would be an oxidation. So you can't have both, so it's just going to be neither.
Oh, okay.
Cool.
Thanks.
This one is a follow-up for the other one, but I couldn't put it on the same page. So. There's a lot of distractions here that Dr. Dottie put for you guys. I mean, that I put for you guys when I made these questions. So next we have this one. So we're kind of just what do you guys think? We're losing a double bond. And we know that alkanes are more reduced than alkenes, and alkenes are more reduced than alkynes. So what do you guys think about this?
Wait, what are we doing?
Is it oxidation, reduction, or neither?
Is it reduction?
So we have a vote for reduction. Does everybody agree with that?
Yeah.
Awesome, great, because this one is reduction. And actually, now that I'm looking at the way that he had the question, he had the options, the options are written out in the question like this. So like A, 1, oxidation, 2, reduction, 3, neither. B, 1 is neither. 2, reduction. 3, oxidation. C, 1, reduction. 2, neither. 3, oxidation. D, 1, neither. 2, oxidation. 3.
And that's because you're gaining hydrogen bonds, right? So it's
Yep, and you
reduction.
gain hydrogen bonds here. Now, what is the answer?
D.
D.
Yep, and the answer here is going to be D. Everybody ready for the next question?
Wait, I'm sorry. Is that a combination of all three of the questions you've asked us?
Yeah.
Oh, okay.
Oh, I was really confused for
Oh, yeah, I was so lost for a second. I was like,
This is 1, this is 2, this is 3, but that's kind of like an example of how he would word the question. So that he's asking you like 3 separate ones, but you have to know like every single one of them to get it correct. Everybody good with that?
Yeah, thank you.
Okay, let's go on to this next one, and this is an IR question. So I'm going to type it up. We have a compound has a strong IR of near 1700 and has 2 peaks in 3-to-1 ratios in the mass spec, and M and M both So this one, if any of you guys get this wrong on the exam, get a question like this wrong on the exam, I will cry. Because you guys had a worksheet question about it. How many of you guys have been going to class? You guys go to class? Definitely go to class.
Yeah.
Yeah,
Sure.
so sure. You guys should definitely go to class. It'll make Dr. Dowdy happy. If Dr. Dowdy's happy, then I'm happy. If I'm happy, then you guys are happy because I hold review sessions. Okay, so breaking this down, what does this 1700 peak mean?
That is like a ketone.
A ketone, so what is a ketone made up of?
A C double bond.
Carbon, oxygen double bond.
Yep, awesome. So it's going to be C double bond O. And then we have a 3-to-1 ratio.
So that's
What does that
chlorine.
mean? Yep. Is chlorine. What would it be if it was bromine?
1-to-1.
Yep. A 1-to-1 ratio means that it is bromine. So if it's a C double bond O, then we can cross out A and D. And then if it is chlorine and not bromine, then that means that our answer is C. Does everybody agree with that?
Do you know why Cl is 3-to-1 and then Br 1-to-1?
I honestly cannot answer that for you, but does anybody have an answer?
It's okay. I was just wondering if there's like.
I personally am not aware why,
Okay.
but
Thanks. I'll just memorize it. That's
yeah.
okay.
I think it's just basically the ratio that the isotopes occur in nature of Br and Cl. I don't know if that made any sense, but
You guys are talking about isotopes. That's great. Whatever helps you remember it. I kind of just, memorized it. It's just like 3-to-1. It kind of looks like, there's like a C and an L. It's like a backwards 3. Whatever helps you memorize it. So over here, this next question. Okay, we have 30 minutes left. We're working pretty good on time. Okay. Did you guys learn about PCC already?
Yes.
Yeah, I didn't go over that when I told you guys the important stuff. I'm pretty sure Casey did a review and she went over like all the different mechanisms. So you guys should definitely watch her review as well. And then we have this option over here. RH, 1, 3, and 4. So what do you guys think that the answers are?
3.
So we have a vote for 3, and why is that?
You just have to know that a primary alcohol is going to turn into aldehyde and a secondary is going to turn into a ketone with those reagents.
When you have PCC, which is a weak reagent, then you get an aldehyde. And then when you have something like CrCO3, which is a strong reagent, then you get a carboxylic acid. And if you have a 2-degree alcohol, and then you get a ketone. So over here, we are dealing with a 2-degree alcohol. And then over here, we have a primary alcohol. So our primary alcohol is with PCC, so that means that we're going to get an aldehyde. Secondary, we're going to get a ketone. So then let's look for our answer. And number 3, we have our aldehyde. And we have our ketone. Is everybody good with that?
Yes.
Yep.
Ready to move on?
Why is CH2Cl2 there?
Probably as just, what is the word I've been using? A catalyst. It's like a spectator, I guess.
Okay.
Okay, next one. So the question is, what is the correct classification of the following reaction? Did it not show up? Love that for me. It says that it's on here. That's extremely annoying. Oh, there you go. Now it shows up. Okay. Okay, so over here we have, this is the reaction. We have a ketone, and now you have a, what's it called? I know what these are called. You guys remember what they're called? Acetyl 1O.
I think it's an ester, right?
An ester, there you go. Yes, and it's an ether without the double C-double-1-O. Sorry, my mind was like blanking, and I was like, there's something related to sulfur as well. Okay, so option one is elimination reaction. B is substitution reaction. C is reduction reaction, and D is oxidation reaction. And so what do you guys think that the answer is?
I see the extra O and I keep wanting to say oxidation, but I don't know if that's right.
So why are you second guessing yourself?
Is it oxidation? It is?
Do you guys agree or disagree?
I think there is
so.
substitution.
We have another vote for substitution. Or do you have we have one vote for substitution.
It's hard because it does add an O, but it also has like another methyl group, so I don't know.
And you are changing the last C, the one in the right, to the O.
Okay, yeah. I think it's substitution then. Is that right? Yeah, I think it's substitution because it's also adding a methyl group.
I wish that the font could change on here. So everybody is just agreeing that the answer is substitution.
I still think that it's oxidation.
Well, that's great because the answer is oxidation.
Oh my god. No, but when someone said the substitution, I was like, oh my god, they're right. Like they actually, like, it kind of does look like you subbed in something.
So over here, if we were to just go ahead and count our hydrogens. So our hydrogens are all staying the same, but we are increasing the number of C to O bonds.
It couldn't
Actually, it's just C to O, just like regular. Yeah, so you have a C bonded to a C, going to C bonded to an O, and it's kind of like you inserted the oxygen. You didn't increase the number of C bonded to C or anything like that. So something that really helps with these types of questions is, again, doing like this type of writing, like how many things there are. So there's still 6 hydrogens, but now there's 2 oxygens, and that will kind of like really put everything into perspective, because you didn't necessarily replace the carbon, you just inserted an oxygen.
This couldn't
So
be.
this one definitely is a tricky question, but the answer is oxidation. Everybody good with that? Do you guys see why it would be oxidation?
Yeah, that makes sense now.
Yeah.
This is a super fun question. This next one, I feel like ozone no lysis questions are always really exciting to do, which also I just realized I didn't really cover that. Just need to know, oh shoot. Oh gosh, what did I do? Do we need to know stereochemistry of epoxides? Yes, you need to know stereochemistry of epoxides, pretty much just for alkynes for this exam, because you guys aren't going over alkenes anymore. But yes, definitely know stereochemistry, which is very annoying to go over, in my opinion.
Can we do one that also has the all reagents? Because in a synthesis, that may be required to use it. The old ones.
I'm going over questions that I know Dr. Dowdy will ask. Like these are really similar to questions Dr. Dowdy would ask, so I feel like it's just more helpful for me to ask you guys questions that I know he would ask, opposed to just like showing you the abbreviations. I think that would be a little bit more helpful, but if we have time at the end, then I can go over them. Cool. Do you guys agree with that, or do you guys just want me to start going over the other stuff?
No, I like the problems, like going over the problems like this.
Yeah.
Okay, so let's go ahead and write out what these products look like. So what is the way that we would be able to get one product from a specific reaction, like ozonolysis, which lyses the product and it kind of splits down the double bond. So how would we get one product?
Has to be symmetrical.
Exactly, it has to be symmetrical. So of these, which one is symmetrical?
B.
B, awesome, and that is the answer. And if we were to actually look at what the product would look like, this is how we would have it. We would have this, like that, O3, H2O, and this as the product. Everybody good with that?
Yes.
And I'm going to do this question one more time, see how much of the information you guys are actually retaining. but I'm gonna put a little twist on it. So what is, let me delete this. So this one is a little bit trickier, I think. What is the answer here?
Is it A?
So I have a vote for A.
I think it's A too.
I have another vote for A.
I think it's A.
Okay, awesome. The answer is A. And what is the other one that we would be able to use?
Is it
NaNH2.
Yep, awesome. The other option is NaNH2, and this is NH3, which has a pKa of 20. And remember, terminal alkynes have a pKa of 25. So this one, just for reference, has a small pKa. I'm not really sure what it is, but this pKa is 18. Okay, are you guys ready for the next question? This is another IR spectrum that I drew with my hand, and it's like really ugly, but I'm gonna show it to you guys anyways. I guess I'll also show it on Notability. So I can just insert the picture here. Okay, I'm gonna go back to Zoom. Share my screen. Okay, and this is another, oh shoot, this is the same question. There you go. So which of the following, or choose the compound that matches the following IR spectrum. You have a 3500 broad peak, and then you have no peak at 1700, which means that there's going to be no carbonyl, which means that we can knock out 1 and 4. So we also see that we have our OH, which means that the answer is going to be 2. Is everybody good with that?
We have like a NH bond because of the first one.
What's the question?
Don't we have like an NH bond because of the 3500, like the first curve?
All right, so that 3500 is our OH bond, not NH. NH, what was NH? That one is 3500 to 3200, but none of the options here have an NH. So that means that this is not an NH bond. That means that it would be an OH.
What about the medium peak that is just above 1500, almost 1600?
But we know that in order for it to be, what is it called? A C double bond O, it would have to be super sharp. Like it would look like this. Does that make sense?
And what about the double bond, a CC double bond?
Give me a second. My bad, you guys. What was the question?
Could it be possible to that one be a CC double bond?
No,
I
it
mean,
wouldn't be
it's very
C
close
double bond
to
O.
1600.
It's like not C double bond O though, because we know that the C double bond O ones are like very, very strong. Like it would look like this. And it doesn't look like that. It only goes up like halfway. And I drew this one, so there's also a possibility that I drew it a little bit too down. Does that make sense?
C double O at 1700 anyways?
Yeah, and it would also be like over a little bit, like here. But C double bond O can be from 1800 to 1650. It's just, and that's like not even 1650. It's like right above 1500. Does that make sense?
Yeah, thank you.
Good at that? Yeah, no problem. So let me go to Zoom. Stop the broadcast. Do whiteboard again. And okay, we have 15 minutes left. I'm just gonna start doing. There's so many more questions that I could have done. I took pictures of these and then I let you guys screenshot them. But if you guys share them, then I'm gonna be super upset. How about that?
Do you know what type of questions could we get in conceptual questions? I mean, the chapter 13 has a lot of, it's almost all conceptual.
Chapter 13 is like all mechanisms, pretty much. So all those mechanisms that are, or wait, your exam is, what is your exam on? 11, 12, and 13? Yeah, so 13 is all those like IR pictures and stuff like that. So I went over a couple of them, and then that was pretty much like the type of questions that he would ask. I'm gonna go ahead and stop the recording. All right, 30 pictures up there. Make this tiny. Okay. So if you watch the recording, I hope you enjoyed it. See you guys next time.